Hello, my name is Roy Simpson. I'm a professor of mathematics at Sumner Server College in Sacramento, California. And this is a second video in an initial review or initial introduction to matrices, whichever it may be. In the first video, we talked about some just basic definitions. What is a matrix? We still haven't talked about the usefulness of them yet, but in this video, we're going to go ahead and tackle the additive properties of matrices. And when I say additive properties, I really mean additive and then the associated inverse operation, which is subtraction. So those two operations go hand in hand. And of course, to start with additive properties, we have to actually define how matrices add. So let's go ahead and start with that definition. How do you define the addition of two matrices? So the direction we're heading is to invent a whole new world of mathematics based on not the addition of just simple scalars like 5 and -4, but instead matrices like A and B. So by definition, we define the summation of two matrices. They first of all have to be the same dimensions, the same size and dimensions. So two matrices A, B, where their dimensions are both m by n, we define that to be a new matrix, C. So as in this definition here, C sub m by n, where the ijth element of C is the sum of the ijth elements of A and B. This is actually fairly natural. This is what you think it should be when you invent a new number system. You try to create things a little to be somewhat simple. So let's take an example here. And in this example, you notice I've created two matrices, A and B. I've just randomly created these here. They're both of the same size. It's incredibly important. They both have 2 rows and 3 columns. So these are both 2 by 3 matrices. Notice how I'm writing the 2 by 3 in the lower right hand corner of each matrix. And that is because it's just traditionally what we do. You don't actually have to do that because people could view this and see their 2 by 3 matrices. However, it's good to write that initially when you're learning matrices. And so by definition, when I take A and add that to B, it should become a new matrix C, where that matrix, let's see, the first element in the first row, so row 1, column 1, will be 3, because that's what was the row 1, column 1 element of A, plus 0, which is the row 1, column 1 element of B. So let me go ahead and show that's the 3 and the 0. That's those two added up. And then you can continue forward with this. You could just say, okay, the row 1, column 2 element will be a -2 plus the sine of x. And of course, that came from this -2 and this sine of x. And we can continue forward this way, right? So I'm going to go ahead and just do the e to the x and the 1, right? And obviously, if you're watching this video, you should be pretty much proficient with mathematics, so you don't actually have to write out all these little steps here. Plus a -x. I'm just going to write it that way. Let's see, 5 plus 6 and 0 plus a -4. Element by element addition is what we would call this. And of course, that matrix C is actually 3, -2 plus sine of x. I leave a little space here just because it's important to let your whoever you're giving this matrix to, let them know that how many elements there are. So I leave big open spaces in there just to be very obvious. There we have it. That is the summation. So addition is very simple. And in fact, because addition is defined element by element, and the elements of matrices are either numbers, scalars, or functions, well then all the properties that we know from addition fold over into the world of addition for matrices, specifically the following two properties. Matrix addition is both associative and commutative. And if you can't recall from your old arithmetic course, These end up being hugely important as you move forward in mathematics. If you do advanced mathematics, the idea of commutativity and associativity are big because they create things eventually called fields, rings, whatnot. So you get into very theoretical structures with having associativity and commutativity in your number system, along with some other things, okay? But for now, we'll just say associativity means that A plus B plus C, the matrix A plus B, then added to C. It's the same thing if we had just taken the matrix A and added it to B plus C. That's associativity. Commutativity is just that you can commute the addition. In other words, you don't have to add A to B. You could add B to A. So that's where the associative property and commutative properties come in. Now, sometimes it is actually useful to go backwards with this. As an example, you might see a situation where somebody might say, well, listen, I have a matrix A that is equal to, let's say, a single column. So maybe it's like a 3 minus sine of x. And let's say the second element, basically the second row, is going to be e to the x plus 5. That was supposed to be e to the x. It looks like e to the plus. Sorry about that. And the bottom one is, say, a 7. You could technically write this as the sum of two different column matrices. If you want, you could say it's 3, 5, and 7. So a scalar matrix, a matrix full of scalars, and a function matrix, which would be a matrix full of functions. Technically, scalars are functions, so there really is no difference between these, but you could break these apart into two different matrices if you want. Not that you often want to, but it is kind of a unique use of the additive properties for matrices. There's also, let me scroll down here a little bit, there's also an additive identity. In arithmetic, your additive identity is 0. That is, you could take the number 0 and add it to any number you want, and it'll bring back the number that you want. So we have that same type of structure within a matrix, and we'll go ahead and define the additive identity. So definition here. Often you'll see in textbooks they'll use bold letters. I didn't really mention this before, but often in textbooks you'll see bold letters for matrices. For example, if I scroll up, that matrix capital A there in a textbook would be bold capital A. But, of course, you're writing things down by hand, so you can't really do bold very well. I suppose I could, but it would be unfair to you. So I could take something like this and put a big bold 0. That's not too bold, actually, but you put a big bold 0 there if you want to. Let me get my pens back. But this is defined to be a matrix of zeros. Dot, 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 and 0, 0, dot, dot, dot. And this is a flexible matrix in that, and there are very special flexible matrices. Is this allowed to grow or shrink based upon the object that you're adding or subtracting against? So this is going to be, if I were to take, let's say, a plus 0. So let's go ahead and take that a from that previous example. So the previous example we had was a was equal to 3 minus the sine of x, and there's an e to the x plus 5. E to the x looks better, but the plus now looks worse, and a 7, right? So if I want to look at a plus 0, it is assumed, when you see that, it is assumed that that 0 is a matrix of the same size as A. So notice here that A is a 3 by 1 matrix, 3 rows by 1 column. So we will assume that the 0 is also a 3 by 1. It's allowed to grow or shrink as necessary. And of course, when you add these two together, you have that 3 minus the sine of x. And you have the e to the x plus 5 finally written correctly, and then the 7. And you're just adding to that a 0 matrix. We also call that a 0 vector, but I'm not really going to get into that now. And then when you add those element by element, it just brings you back to a. 3 minus sine of x, and e to the x plus 5. and a 7, which is the same thing as A. So that's why we call it the additive identity, because when we add it to any object, it brings back, specifically matrix that is, it brings back the original matrix. So it is the identity. It is often the purview of like a first course in linear algebra where you prove a lot of things with additive inverses, additive identities. Additive identities and the commutativity and associativity laws. You end up playing with those for a little bit, and they are as simple as I've made them out to be. But you have to be somewhat meticulous in how you do a proof in mathematics. So just letting you know that for general, if I wanted to prove, for example, that as I scroll up here, where do I have it? That matrix addition is associative and commutative. Let's say I wanted to just prove that it was commutative. The proof is not as simple as just saying, well, listen, A plus B has to be B plus A because you're adding elements. You can't do that. You have to take a general element, the ijth element of A, and add that to the ijth element of B, and use the fact that those are both scalars or possibly functions, and that on the scalar or function level, we have commutativity, so that aij plus bij is the same thing as bij plus aij, and that is true for all elements, so therefore a plus b is equal to b plus a. One last little statement here, and let me scroll down to make this statement. We do have an additive inverse as well. So before I get to that, I want to just kind of as a side note here, and my notes are usually done in purple, so I'll just do a little note here. Note. A minus B, so subtraction also exists with matrices, but it's just the same thing as saying A plus the opposite of B. Now that's kind of weird because I haven't talked about multiplication yet. So if you bear with me for a moment, it is a negative B just swaps the signs of every element in B. So as an example, and we'll talk about this more in the next video, but it just goes along with addition so nicely that I have to kind of talk about it here. I'll just create simple matrices. 1, 1, 1, 1 is what A is, and B will let be 3, -2, 1, and 8, or something like that. Okay. A minus B would be the same thing as A plus a negative B. And for now, I will just say, I'm not going to write it that way, I will just say that when you have a negative in front of a matrix, that means you're switching the signs of each element in that matrix. So this would be A, which is 1, 1, 1, 1, plus the opposite of B. So I'm going to swap all those signs in there. So I have a -3, a +2, a -1, and a -8. And now we can just do traditional element by element addition here. So you get a -2 and a 3 and a 0 and a -7. Okay. And notice these matrices, again, were of the same size. So you cannot do this addition. The only way you can do addition is if they're the same size. Obviously, if you had a matrix that was 2 by 2 and you're adding it to a 3 by 3, there's going to be elements missing when you're adding it to, let's say, the third row first element of the second term. So now I've defined or talked about the difference of two matrices, I can now introduce the last of the additive properties. So this will be 4 properties in this video that matrices satisfy commutativity through addition, and the additive associativity, also the additive identity. So we have those 3, and then this very last one is called the additive inverse. And I decided to write this as a theorem. If you let A be any matrix, then there exists some matrix B such that A plus B is equal to 0. Remember, 0 is the additive identity. It's just, I want to write it this way because in theoretical mathematics, higher level mathematics, this is kind of how you think of things. You think of things as, I need associativity for addition. I need commutativity for addition of objects in this world of matrices. I need an additive identity so some type of 0, which we know we have. But you also need an additive inverse, something that will undo a matrix. If somebody hands me a matrix A, I want another matrix so that when I add them together, it brings me all the way back to the additive identity. So we're given a matrix A, and we want a matrix B such that we get the additive identity. And of course, everybody's probably screaming right now saying, well, I already know what the additive identity is. It's just going to be negative A. So the additive identity is equal to negative A. So a cleaner way of writing that is that A plus a negative A will equal 0. Again, it seems so basic when you're first learning about matrices, but this idea that you're creating a kind of a new number system with new types of numbers, these numbers are called matrices, and that you have to, that a number A, let's just say it's a number A plus the opposite of that number A becomes 0. That may seem like, well, duh, of course to you, but that actually is not always true. There are some systems that you can create where that won't work out. So just letting you know that this is a very basic property we need to have, but it's not always true. But at least with matrices, it is. That's it for this video. Very simple, kind of straightforward. In the next video, we'll talk about multiplication.